No, we skipped over 5.1. We did that graphing calculator sheet instead. And what that activity did was sort of set up what are exponential functions and how do you graph them. So we have sort of two main types of exponential functions. An exponential function is any equation where the variable is in the exponent. So you got y equals 3 to the x, y equals 7 to the x, y equals half to the x. And there's sort of two main graphs that appear. Anytime your base is bigger than 1, so if I graph y equals 2 to the x, the graph will look like this. And this is one of the things from that activity that I hope you started to realize. That all of our graphs have this sort of shape. A couple of key characteristics that we can take from that graph. No matter what the base is, 2 to the x, 3 to the x, 4 to the x, if you plug in 0 for x, what happens when your exponent is 0? What is 2 to the 0? It's equal to 1. 3 to the 0 would equal 1. 7 to the 0 would equal 1. So no matter what our base is, we always have the point 0, 1. Now, if we wanted to put another point on here, we could think of a table of values. If I plugged in 1 for x, what would y be? Well, 2 to the power of 1 is 2. So those become two key points that we're going to put on any exponential graph. I mean, if we had y equals 7 to the x, if I just change this from a 2 to a 7, the only thing that would be different, instead of 1, 2, I'd have 1, 7. And if I changed it to 9 to the x, I'd have 1, 9. And if you wanted to, you could put more points on. Like if I put x is 2 in there, I could plug in 2 for x, and 2 squared happens to be 4. And if I put x is 3 in there, 2 to the power of 3 is 8. So I could put more points on there if I'd like, but the key ones for any exponential graph is you'll always have 0, 1, and you'll have 1, whatever the base is. The other thing that exponential functions all have is they all have an asymptote at y equals 0. So these become our parent graphs, and what we're going to do with these parent graphs is all the transformations right from our first unit that we did on transformations. We are now going to do all of those transformations with these parent graphs. So it's sort of going to be a review of that first unit, and we just have new graphs that we start with. Now, anytime that your base is between 0 and 1, and that's what it says right here, then the graph is decreasing. So for example, if I were to graph 1/5 to the x, thank you. If I were to graph y equals 1/5 to the x, again, set up my axes. And no matter what the base is, you will always have 1, 0, 0, 1. That was close, eh? When x is 0, y is 1. But in this case, your exponential graph will be decreasing. You still have an asymptote at y equals 0. And the reason it's decreasing is because now if I plug in 1, I will get 1, 1/5, which is less than 0, 1. And so that's why that graph is decreasing. The other thing that you might have seen in that graphing calculator activity is that 1/5 is the same as 5 to the negative 1. And so if I write 1/5 as 5 to the negative 1, then this equation is the same as 5 to the negative 1 to the x. And if I use my exponent rules, that's the same as 5 to the negative x. What does 5 to the negative x do as far as transformations go? Where the x is, we now have a negative. And if the negative is where the x is, that's a reflection over the y-axis. So if I think of this graph, 5 to the x, looking like this, with 1 comma 5, and if that graph is flipped over the y-axis, I now have the point negative 1 comma 5, and that shows up in the 1/5 graph. So some connections between transformations and our graphs. But for the most part, you're going to say, I know that all exponential graphs either are increasing like the one on the left or decreasing like the one on the right. And you will find that 80–90% of ones will be like the one on the left, increasing ones. Not very often that we get the fraction ones, but it comes up sometimes. And so we need to be able to see all of these graphs and then deal with the transformations that go with them. So we have to be able to quickly graph these parent ones, and that's what we're going to do in example 1. Happens to be that the one off to the side is the one that's not quite as common, one with a fraction. So here we have an exponential function. It's the basic one with no transformations. We set up our axes. We know that we'll always have, for every single exponential, we will always have 0, 1. We will always have an asymptote at y equals 0. And since this one is 1/3 as the base, that means when we plug in 1, we will get 1, 1/3. And by doing those 2 points, you'll be able to tell this one is a decreasing one. It has to be going down, because the only way that you can go to these points is down like that. So I guess that determines that our shape is going to look like that. Once we've got the graph, we can answer each of these questions. What is the effect on y when x increases by 1? Every time we increase by 1, y gets multiplied by 1/3. That's the effect of an exponential graph. An exponential graph is always multiplying by the same number over and over again. Is this one increasing or decreasing? It's decreasing. The intercepts, there's only a y-intercept at 1. There's no x-intercept because we have an asymptote on our x-axis. So our equation of our asymptote, that's just y equals 0. The domain of the function, the domain is everything in an exponential function. There's not a value of x that's not allowed. So our domain is everything. And our range, because there's an asymptote at 0, y is bigger than 0. It can get as close to 0 as it likes, but will never touch 0. So we need to be able to graph our parent graphs first, so that when we do our transformations, we can do any transformation we like. So if you want practice with parent graphs, 3, 5, and 7.